Hello, I'm Sala, and in this video we're going to simulate the solution of the partial differential equations governing the dynamics of this tubular heater with constant flow. We will briefly review which was the partial differential equation and which was the Laplace transform solution in transfer function form, and then we'll deal with the simulation with the control system toolbox. Under several simplifying assumptions, one-dimensional flow and no viscosity, this is the partial differential equation that governs the physics of the tubular heat exchanger. We have this transport term, volumetric flow divided by the cross-section is the linear speed of the fluid, the transport speed. We have this term modeling the thermal conductivity with respect to the outside temperature. We are assuming that outside temperature is 0. We are setting the origin of our temperature coordinates at that outside temperature. And then we have this term associated to the resistor that is heating the fluid as it travels from left to right. So if this were not present, we would get what is called the transport delay equation. And if we wished to solve only for the steady state in which temperature profile does not change in time, then we get an ordinary differential equation in the length variable, this one here. So that equation has an exponential solution called lambda distinct, and the pole in length coordinates, of course, not in time response, it's minus lambda. So we get this famous steady state heat exchanger formula when everything is constant. If I think in this partial differential equation in which I just name VAB, the coefficients, in order to avoid dealing with a lot of physical parameters, by the Laplace transform method on the time domain, we can obtain this solution to the partial differential equation in transfer function form. And we get, of course, a different solution for each different position. If we set inputs to constants and we set S to 0, then we obtain the DC gain final value, and we get the same steady state solution as we discussed before. And if we name phi L divided by the speed, so total length divided by the speed is the washout time, the time it takes for a molecule of the fluid here to wipe out everything inside and come at the right hand side, then we can show that this is the transfer function matrix that governs for constant flow the dynamics of the outside temperature. Details of the partial differential equation modeling and solution are in other materials in this collection. So this transfer function matrix is just a convenient notation to glue together two transfer functions. This is the transfer function for heat power, assuming that heat power is uniform along the length of the heat exchanger. And this is the transfer function for inlet temperature. And the output of this transfer function representation is the outlet temperature. This is clearly the Laplace transform of a delay operator. Of course, the transport delay. Phi is the flushing time. This is a gain, so it's kind of easy to guess what it will be, the time response. But in here, it's kind of more complicated. But we'll use the control system toolbox of Matlab to simulate these things. So let's go. Control system toolbox is ready to simulate systems with time delay, so we are happy. We don't need any approximation. We'll set some values for physical parameters, this kind of things, and we'll compute these B and A parameters of the solution following the formulas below. So this is B, this is A, total volume, and the linear speed is the 0.19 meters per second. The flushing time is 10.7 seconds. And this exponential in here is the gain, the attenuation that the inlet temperature variations is seen at the outlet due to heat loss. We'll see that if kappa is 0, then this exponential will be 1. That will mean a perfectly insulated pipe. But in this case, our pipe is not perfectly insulated, so we get 62% of the inlet temperature variations observed at the outlet. 38% of those increments have gone to the outside environment because of heat conduction along the walls of the pipe. With these 4 lines, we will input in the control system toolbox objects the transfer function for the inlet temperature, this exponential times the exponential of Vs, which is the delay. And then this thing is exactly the same as this one. So it's kind of 1 minus the inlet transfer function times this first order dynamics. And that's what we write for the heat power transfer function. So this is the partial differential equation model in transfer function form in Laplace domain. If we now evaluate the step response to a steep increment in inlet temperature, then we get the delay of this 10.7 seconds flushing time, and we get this gain of 0.62 attenuation of the inlet temperature variations due to heat dissipation to the outside environment. So we see, as expected, a delay of the flushing time and the gain lower than 1. If we now plot the heating power step response, I will also add this first order dynamics, this one, which multiplies this delay stuff, because we'll see that the effect of this left factor is truncating this first order step response. Indeed, the red line would be the first order response. It will be, let's say, the time response of a longer heater, in which the heating power acts in a traveling molecule of fluid for a longer time. I mean, we are not modeling any longitudinal heat conduction, so it's kind of each slice of our heat exchanger is thermally insulated from the slice before and after it. So the only thing that this slice feels while traveling along the pipe is that it has a heating power hitting it constant, because we are assuming uniform heating, and it also has a heat loss to the outside constant temperature. So each slice, as it travels through the pipe, it's just a volume of water being heated with a constant power and losing to a constant heat reservoir within the environment. So it has a first order time dynamics for it, if it doesn't know it's moving, but okay, we know that it's moving, so it's heated with that fast first order dynamics until it reaches the end of the pipe and stops being heated anymore. So that interpretation makes that we are now only looking at the hotel temperature. If we are cold inside, as the pipe is flushed, we are receiving samples of slices of fluid that has been heated for a longer time, until of course everything has been completely washed out and all the fluid has been renovated, and we get the sample of fluid that has traveled the whole pipe. So this is the response we see, a first order response truncated at the 10.7 washout flushing time. If the pipe were longer, we would get this first order response for a longer time, until, let's say, it would be infinitely long, in which we would actually get a first order system. Next simulation we are going to carry out is setting a equal to 0. So this will not be here, and the exponential of 0 will be unity. So we'll get this kind of transfer functions. This will be a pure delay, and the first order system we are going to truncate will be just an integrator, a ramp. Let's see it in Matlab's plots. We put 0 to the thermal conductivity. The A coefficient is 0. Flushing time, of course, does not change because the flows have not changed. And now the longitudinal attenuation due to losses to the environment does not exist. So the effect in the outlet temperature of the inlet temperature increments is 100%. And indeed, now we get that after the flushing time transport delay, we get 1 degree increment at the outlet. If the inlet temperature increments 1 degree, as expected, it's perfectly insulated. And regarding heating power step response, as it's perfectly insulated, if the pipe gets longer and longer and longer, the slice of fluid traveling through that pipe will get more and more and more heating without any temperature loss. So temperature progressively increases, but when that slice of fluid leaves the pipe, then it no longer increases. And if we start with a cold pipe, and the fluid is circulating, of course, then the first samples of fluid have been heated for a very short time, but as time passes, then we receive at the right end samples of fluid that have traveled the whole length of the pipe, and hence they have been heated for the whole flushing time. So this truncated ramp is the type of response that we would see. So let us summarize. In this video, we have analyzed the behavior of this couple of transfer functions. The inlet temperature transfer function is a delay plus a gain and attenuation. The more conductivity of the tube wall, the larger the attenuation. And the heating power transfer function, its step response, sort of a truncated first order response, or in the case of a perfectly insulated pipe, it's a truncated ramp. With suitable inverse Laplace transforms, we could have computed the time response. In fact, computing the step response of this system analytically with inverse Laplace transform is a common exercise in the first courses in automatic control. We just used Matlab's step response to get an intuition on what that step response meant. Okay, this is it. We finished here. Thanks for watching.